have the results, which I think actually are interesting. I hope to be able to convince you by the end of the talk this morning are also interesting. What we're interested in doing is taking syngas and making alcohols out of them, higher alcohols. So not just methanol, we're interested in making C2s, C3s, C4s, and higher alcohols that we can make them. These are useful by themselves as extenders for gasoline, also as a source of oxygen. As you'll see later on, as I go through the talk, you can take a mixture of methanol and isobutanol that are made over these catalysts and make MTBE out of them. Here's sort of a series of highlights as to what you have to look out for if you want to make alcohols from syngas. The first thing is if you want to make alcohols from syngas, and you particularly want to make methanol from syngas, the materials I'm going to describe to you are not the catalyst that you want to use. Methanol is made very efficiently from syngas, and it's an excellent octane enhancer, but by itself, it has problems. The first thing is, of course, it's very hygroscopic, so it absorbs water, and water in the gas tank, as you know, is a problem. And also the apparent vapor pressure of the mixture is increased, methanol being quite a volatile substance. You can use methanol in combination with other alcohols, preferably higher molecular weight alcohols, and the combination of the two is an excellent gasoline extender. The lower alcohols, methanol and ethanol, raise the octane rating, and the higher alcohols act as a co-solvent, allowing good miscibility between the methanol and the rest of the gasoline. And in general, longer chain alcohols are better co-solvents than the short chain ones, as you might expect. As I mentioned in passing, unless an extremely effective mixed alcohol catalyst is discovered, methanol is best made separately using a different catalyst system, the copper zinc oxide or variations thereof, which are a lot more active and a lot more selective for methanol. And the most effective higher alcohol catalysts will be those that maximize the higher alcohols and minimize the methanol production, as you might imagine. And if you can do it, a 1-to-1 mole ratio of methanol and isobutanol can be used to make MTBE. Here are the major reactions that go on over the catalysts. The first is syngas to alcohols, and water is produced as a byproduct. The major competing reaction, which we don't want to do in this case, we don't want to do Fischer-Tropsch chemistry, but Fischer-Tropsch chemistry does occur over the catalyst. Again, the production of hydrocarbons and water, and the catalysts that I'm going to talk about today are excellent water-gas shift catalysts. So the water that's produced in the first two reactions reacts with CO, one of the reactants, to produce carbon dioxide and hydrogen. In contrast to some Fischer-Tropsch catalysts that don't show water-gas shift activity, the catalysts I'm going to talk about today do. Fuel alcohol catalysts have been around for a long time. The ones that have been developed more recently are the copper-based catalysts, very similar to the methanol synthesis catalysts. And essentially what you do is you add alkali to the copper, and that does two things. First of all, you start to see the higher alcohols, and secondly, the activity is knocked down by an order of magnitude. So this is the reason why you don't want to make methanol this way, because the catalyst is very inactive in comparison to a traditional methanol catalyst. You can maximize the higher alcohols by adding some sort of a Fischer-Tropsch metal in there, which will give you the higher molecular weight derivatives. So for example, you can add small amounts of cobalt, and IFP developed a copper-cobalt catalyst that does make higher alcohols. The alcohols that you see off this kind of a catalyst are linear alcohols, and they follow a classic Anderson-Schultz fluoride distribution So you make an awful lot of methanol, some ethanol, less normal propanol, less normal butanol. And you can regard this as occurring by a so-called classic CO insertion hydrogenation mechanism. And there are other materials also that give you this sort of product distribution. Supported rhodium catalysts. I think Bill Bartley's here in the audience today. Union carbide, he's worked on some of these. And the molysulfide catalysts that have been jointly developed by Union Carbide and Dow. But again, they give you a lot of methanol, a lot of ethanol, and the activities are low because they're modified with alkali. The original higher alcohol catalysts, and now we're going back to the Second World War, it's amazing how moments of crises give rise to inventions, and the Germans were very inventive out of necessity to make chemicals in syngas back at that time. The original higher alcohols catalyst is actually a modified spinel oxide structure where addition of alkali to the spinel resulted in the formation, instead of methanol, which is what they originally wanted to make, they noticed they made higher alcohols from this. My grandfather, Wayne Nauman, who's in the audience here, informs me that the spinel itself is magnesium aluminate. And that's, again, an AB2O4 structure. But A and B can be the same metal. And John Briggs, who is our resident rust expert at Union Carbide, reminds me that Fe3O4 rust does in fact have the spinel structure. So it's a very versatile structure where you can put in the same or different metals, different oxidation states, and you can get different chemistry out of it. The interesting thing about this series of catalysts is, first of all, they're high temperature catalysts. They can operate at 400 degrees centigrade and above. You cannot operate copper catalysts at this temperature because the copper sinters very, very dramatically. And the other interesting thing is you do not see an Anderson-Schultz fluoride distribution of alcohols out of these catalysts. You see, first of all, you don't see linear alcohols. You start to see branched alcohols. And interestingly, they're the 2-methyl branched alcohols. And the first alcohol in that series is isobutanol. So you actually start to see lots of methanol and isobutanol as primary products, and this is thought to occur via an aldol condensation mechanism to form the carbon-carbon bond, followed by hydrogenation. So the reason why you see the different product distribution is because you have a different mechanism to form the carbon-carbon bond. When I entered the program, we sat down and tried to come up with some criteria on how we were going to approach putting a new spin on some quite old chemistry. And these are the assumptions that we made up front. And we can discuss these after the presentation if you like. The first thing is that linear alcohol catalysts are a less attractive choice because they give you the Anderson-Schultz fluoride distribution, and therefore they make too much methanol. And this is an inefficient way of making methanol. Therefore, the isoalcohol catalysts are the preferred ones to look at. They give you the non-Schultz fluoride distribution, and if you can be clever enough with the catalyst, you should be able to produce a catalyst, at least theoretically, that can make a 1-to-1 mole ratio of methanol and isobutanol, and therefore go on to make MTBE. Higher temperature operation is preferred. And the reason for that is based both on kinetics and thermodynamics. We're looking at a sequential reaction sequence, and therefore, as we go up in temperature, the kinetics of the subsequent steps increase. So as we go on, we should start to make more and more of the products that are further along in the reaction chain. And the other thing is under reaction conditions, methanol synthesis is essentially at equilibrium. And as we go up in temperature, the methanol equilibrium shifts back to CO and hydrogen. So the combination of kinetics and thermodynamics is on thermodynamic grounds, you're making less methanol to start with. And on kinetic grounds, the methanol that you are making is being converted on to the higher alcohols. So there's an advantage both by kinetics and thermodynamics. And finally, we're not going to have copper metal, because if we want to go to higher temperatures, we can't have copper in the formulation. So the catalysts that we've developed here at Carbide are based on the spinel oxide, and the one that's most commonly regarded is the zinc chromite. They operate at 400 degrees and above, and they produce the non-Schulz-Flory distribution. The way that we go about utilizing this class of materials is obviously we'll change the metals that are present in the support. We do add promoters. Alkali promoters are added, and copper metal is absent. Here's a slide showing you just how radically different this is from a classic Schulz-Flory distribution. This is for a catalyst that tested under what I would regard as our normal test conditions, 400 degrees centigrade, 1,000 psi syngas, and the ratio of hydrogen to CO is 1:1. And space velocity is about 12,000. And the numerical designation shows you that this is one of the catalysts that Dick made early on in the program. You can see that the catalyst does make methanol, makes a little bit of ethanol. The C3 here is mostly normal propanol, although under some conditions we do see the iso product. And C4 is almost exclusively isobutanol. From this you might infer that the slow step in the reaction is the C1 to C2 step, going from methanol to ethanol. With our first step in making the catalyst, this is the catalyst for the product distribution that I just showed you. And what I've done here is I've put this up with a comparison of what I would regard as the most nearly commercial catalyst that's out there, which is one that's been developed by Air Products that's been tested down at the LaPorte pilot plant facility in Texas. And that is a copper cesium based catalyst. It can only go up to about 350 degrees centigrade. Really, it can't go much above 300 degrees without catastrophic deactivation. They operate up to 2,000 psi, relatively comparable space velocities. They operate at a very CO-rich syngas mixture, such that you might get out of coal-derived syngas. The weight percent isobutanol is around about 20%, and the rate is somewhere between 50 and 100 grams per kilogram hour. Notice that this catalyst still makes an awful lot of methanol. So the methanol to isobutanol mole ratio is no lower than 8. With the catalyst that we first looked at, we're operating at the higher temperatures, comparable pressures and space velocities, using a less CO-rich syngas feed. We end up with a catalyst that's more selective to isobutanol at a relatively reasonable rate compared to the state of the art. But now we have a methanol to isobutanol ratio of about 3. What I'd like to talk about now is the effect of process conversion on catalyst performance, both by varying space velocity and by varying temperature, and then the effect of the process parameters on the catalyst performance. So we'll look at the effect of space velocity, temperature, pressure, and syngas ratio. And we'll talk a little bit about some of the problems that arise when you go to low syngas ratios at high temperatures, and then a little bit about how we surmount that, and what sort of productivities and activities we get when we go to both high temperatures and high pressures. I want to talk a little bit about why we want to do that. But we'll get to that after I've discussed some of the process parameter results. Here's the effect of process conversion. And at the top here, it's by changing space velocity. In the bottom graph, it's by changing the temperature. You can see that as the conversion goes up, the selectivity to total alcohols falls quite dramatically. So When we're at low conversions, around about 15% conversion, we do have very high selectivities to alcohols, somewhere around 70%. But as we push the conversion much above 30%, the selectivity falls to about 30% selectivity to alcohols. This is actually a function of the alkali content on the catalyst. And by increasing the alkali content, we can push the higher conversions and yet still keep the selectivity to higher alcohols. But the reason why I put this up is because it shows you an inherent problem with the catalysts of this type. As you want to push the thing to higher conversions and the heat load within the catalyst bed increases, the thermodynamics want to make hydrocarbons. All right, so this is always going to be a persistent problem. I'm going to show a series of graphs now, so I'm going to spend a little bit of time familiarizing yourself with the format here, because the format's going to be the same as we go through here. The top graph is going to show whatever parameter we're interested in, and it's going to be a plot of the alcohol rates. The open circles is the total alcohol rate, and the closed circle is the isobutanol rate. On the bottom graph, I'm going to show the methanol to isobutanol mole ratio, which, if you like, is a figure of goodness as to the direction that we want to go. And the lower that number is, the better. We can see here that as we decrease the space velocity, the alcohol rates fall. But the interesting thing here is that the methanol to isobutanol mole ratio also falls. The reason for this is as we increase the residence time, going to lower space velocity, we allow the consecutive reactions to increase. So while the overall rate decreases, as you would expect, the amount of isobutanol increases. So the methanol to isobutanol mole ratio falls. However, you can only play this game for so long, otherwise you're just not making enough product per unit time. Here's the effect of temperature. And you can see here that temperature is not a very good handle on increasing reaction rate. If you look at the total alcohol rate, it actually falls with temperature. And this is a consequence, remember, of the fact that the methanol equilibrium is disfavored at a higher temperature, so we're making less methanol. However, the isobutanol rate does increase modestly because of the consecutive reactions on methanol. The methanol to isobutanol mole ratio therefore falls. Here it's about nearly 4, and when we get to high temperatures, we're down at this ideal 1-to-1 mole ratio of methanol to isobutanol. The problem here is that the catalyst selectivity to alcohols also falls. So we're making an awful lot of hydrocarbons when we get to the higher temperatures. So again, there's this trade-off. The biggest handle on reaction rate for this system is pressure. And you can see here that as we increase the pressure from around about 700 psi up to about 1350, the alcohol rate triples. Goes from about 100 grams per kilogram hour of total alcohols nearly to 300. And the isobutanol rate also increases. It about doubles. However, as you can tell from those two lines, the problem is the methanol rate is increasing faster than the isobutanol rate is. So even though we're getting this big increase in rate, the methanol to isobutanol mole ratio, which was down around 3, by the time we get up to about 1350 psi, it's now climbed up to 5. So while the overall rate of the reaction is increased, we're making more of the undesired methanol product. The selectivity of total alcohols, by the way, remains relatively constant over this region. Here's the effect of changing the syngas ratio. For those of you who aren't familiar with the standard methanol catalyst, it operates at very high hydrogen to CO ratios, somewhere 3, sometimes as low as 2. But that favors methanol synthesis. As you go to lower ratios, you increase the CO in the feed, you start to favor the higher alcohols. And what happened here is you can see that as we go from syngas ratio to 2 down to 1, the total alcohol rate falls and the isobutanol rate maybe rises slightly. However, when we hit the 1 to 2, we get a very dramatic increase in the rate. And it would be wonderful if we could hold it at that, but the reactor plugs. And persistent attempts to run the reaction under these conditions plug up the reactor again and again. And the problem is we're now getting other chemistry occurring, and it's CO disproportionation, the so-called Boudoir reaction, where CO disproportionates to form carbon and CO2. And the carbon that's deposited plugs the reactor up. Before it actually plugs it up, there's some carburization of the stainless steel tube occurs, and we get flaking of nickel and iron from the tube wall, which is carried downstream and starts to be deposited on the catalyst, which now becomes a very, very active Fischer-Tropsch catalyst. And when we discharge the catalyst, it's covered with a beautiful wax, which we can analyze by GC mass spec, and it has a molecular weight C24 through C48, wonderful linear Fischer-Tropsch wax. Unfortunately, it's not what we want to make. So there are intrinsic problems with running at 1 to 2 syngas at 400 degrees centigrade because the tube wall now becomes a catalyst for undesired reactions. The way you can get around this is to put in a copper lining, so you don't allow the iron to do its chemistry. And then you can operate the catalyst above 400 degrees centigrade. I'd like to take this opportunity then to summarize what we learned out of the process parameter studies. The first thing is that operation at low syngas ratios results in reactor fouling. And you also actually see incomplete hydrogenation of the products. This could be a consequence of the fact that we have a copper lining also, because copper is known to be, especially at higher temperatures, to be a good dehydrogenation catalyst. So we're not quite sure that we've decoupled those two effects. As you go to lower space velocities, it's in the direction of goodness in terms of the isobutanol selectivity, but the overall productivities are unacceptably low. So we really have to operate at about 2,000 space velocity or higher. We would like to operate at 400 degrees centigrade. However, we have to worry about this hydrocarbon formation. And if we operate at higher pressures, we're going to get more alcohols with no loss in selectivity, but we're going to make methanol rather than the higher alcohols. So what combination here is going to get us to the desired effect? And I guess the best way to look at it is with this rather simple pictorial representation. As you go to higher temperatures, hydrocarbon formation is highly favored. The methanol rate goes down and the isobutanol rate increases. As you go to higher pressures, the hydrocarbon rate actually falls, the methanol rate increases quite dramatically, and the isobutanol rate increases. So what we have here is we have two very strong, very powerful, very favorable reactions that are going on. Methanol synthesis and hydrocarbon formation. What we have to try and do is balance these two out against one another, so if you like, the isobutanol can sneak in between the two. So what we would expect to happen here is the combination of higher temperatures and higher pressures would favor isobutanol and would not particularly favor any one of the other two major competing reactions. And this is exactly what we see. Here's the similar table to the one I showed you before. This is the data that I already went over, which was our first attempt with our catalyst. We went back and modified the alkali level on the catalyst, And then we went up to 440 degrees and 1500 psi. You can see here that the ratio of methanol to isobutanol is further decreased, but now the isobutanol rate goes up by a very significant amount. We're almost up to 200 grams per kilogram hour of isobutanol. And at these rates, the methanol to isobutanol ratio is down around 2.2. This is, in my opinion, the best catalyst that's out there right now. The problem, though, is that we are operating at higher temperatures, 440 degrees, so the reactor configuration is now going to become an issue. Just exactly how are we going to operate this system? I've been talking about a fixed bed reactor. It might well be that some other reactor configuration is the best way to operate this. And the temperature, the pressure is, I think that's an acceptable pressure, at least for commercial operation. But the temperature is still an issue, at least for operation. So what do we have to do here? I think, in terms of catalyst performance, we still have to increase the isobutanol rate. I don't think it's going to be a large increase, but I think we probably need to be getting the isobutanol rate up above 300 grams per kilogram hour. So by a factor of at least 2, I believe. The methanol to isobutanol mole ratio really should be 1 or lower. Okay, we would really like to make higher alcohols and not methanol with this catalyst. And if we need to make some methyl ether out of the product mix, we can take methanol from another source and add it. Process conversion. Right now we can get above 30% syngas conversion at acceptable selectivities. That 440 degrees, 1500 psi, the process conversion there was around about 30%, and the selectivity was about 64%. And that's all acceptable. We'd like to get the process conversion up probably to about 35 to 40%. We still have not yet addressed the issues of catalyst life, or how are we going to make this catalyst that we now make on the gram scale into a commercial charge. And as many of you are aware, this itself is an art. We're in the process of doing catalyst characterization so we can hopefully get a handle on structure-property relationships of the catalyst. I've already alluded to the fact that reactor configuration is now an issue. We have to figure out just exactly how we're going to operate the catalyst. And then how are we going to integrate the overall process so we can have an economical plant that's out there. All right, that's all I'm going to say for right now. Again, I'd like to acknowledge Dick Nagaki, who is responsible for the breakthroughs in catalyst preparation that led to the discovery of these catalysts. Paul Rupert, who's a person who has done most of the catalyst testing and came up with the way of developing the copper line tube, which allowed us to go to the higher temperatures. Jerome Hornbuckle, who was the technician who actually made the catalyst. Dwayne Dunbeck and Jim Schreck, Carbide, for their helpful input into both management and direction of the program. And Gary Steigel from PETSI, Department of Energy, who provided the money. I'd like to thank you for your attention, and I'll attempt to answer any questions that you might have.
Are there any questions? I have one that I want to ask.
Sure.
As you know, that in the methanol synthesis, CO2 has profound effects.
Right.
And you were talking about how your catalyst is very active for water gas shift. I was wondering whether or not the effect you see with syngas ratio is not maybe an effect of CO2. You're actually making more or less CO2 as you change your ratios.
We have actually fed CO2 to the catalyst. And what it does is it significantly depresses the activity of the catalyst, as you might expect, but it also makes it a very selective methanol catalyst. And An interesting observation is after you fed CO2, you take the CO2 off. Okay? The catalyst does not recover immediately. There's a long, slow activation period that occurs until it gets back up to making the higher alcohols. The first big kick that you see is in methanol formation. So it's almost like there's a carbonate layer on the surface that when you take the CO2 off, starts to decompose into CO2, and that CO2 makes methanol. So if I had to speculate on a mechanism for methanol formation of this catalyst, I would have to say that I believe that CO2 is the intermediate here that's making methanol. But in terms of the deleterious chemistry, the carburization and the Fischer-Tropsch chemistry, I don't think that's due to CO2.
In your yield, where you were comparing Air Products and your two catalysts, there must be different conversions or something, because theirs was producing more in one case than one of your catalysts. There was very little difference in conversion, or in the amount that you were saying was percent formed, and yet big difference in amount produced per kilogram hour.
Well, I don't think there's a big difference in the amount produced. Let me put that up. You can tell me what to say.
Well, maybe I don't understand. If you look at the isobutanol weight percent, they're essentially the same at the same flow rate. No, the last two.
Over here?
Yes. And yet the isobutanol rate is...
Oh, the conversion is much higher here.
That's...
Much higher. This conversion
Yes,
here
okay.
is about 13 to 14% conversion, and up here it's nearly 30. So the conversion's about doubled.
And so Air Products conversion is much higher than what you're running.
Well, no, yeah, I presume it is. I don't have their conversion numbers on here, but yes, yeah, I would imagine.
How did you? Good.
Yeah, I was wondering if you could comment on the selectivity in terms of the mechanisms of these reactions in regards to the catalyst. What you feel is responsible for this selectivity.
Well, first of all, I mean versus the isoalcohol production versus normal alcohol.
Right, and C4 and C1.
Right. In terms of the mechanism, we believe that over these catalysts that it's a base catalyzed aldol condensation that's producing the carbon-carbon bond. Okay. That's different from the so-called classical CO insertion hydrogenation mechanism that you think about when you think about normal carbonylation, both for homogeneous catalysis and heterogeneous catalysis. The interesting thing here is that this must be a base catalyzed aldol, not an acid catalyzed aldol, because the presence of acid here gives you hydrocarbons and not oxygenates. The fact that we have a heterogeneous catalyst, I think, is in some ways to our advantage here, in the sense that you can't build up too large of a molecule on the surface before it's crowded out, and the rate falls just dramatically because you no longer have access to the catalyst surface. So we do see higher products. We do see the corresponding C5 and C6 alcohols. They're always the 2-methyl alcohols that we see. So the branching is not dramatic. Okay, it's always at that second carbon atom, the methyl group on there. But we can see the higher alcohols, and we've gone back and we've fed some alcohols to this. We fed methanol, ethanol, the propanols, and we do see more of the higher alcohols. But again, it's this very narrow, highly specific production of isobutanol that we see. I think I alluded to the fact that we think that CO2 is the intermediate that forms the methanol. And we think the slow step in the reaction is the methanol to ethanol production. But actually, at these temperatures, the subsequent reaction steps are roughly equal in rate, fortuitously, I think. So we can feed ethanol, for example, and we can get a 3-fold improvement in the isobutanol rate. but we can feed normal propanol and get a threefold increase in the isobutanol rate. So whether we feed ethanol or whether we feed normal propanol, we see roughly the same increase in rate, which is not something you would have expected ahead of time. You would have thought ethanol would have been far more effective. But it turns out, under the reaction conditions that we're running at, they're about the same.
I have two questions.
Sure.
Number one, how could you circumvent that problem of the reactor sites reacting with the products and giving off nickel and stuff like that, depositing on the
Oh,
catalyst?
sorry. Maybe I went too quickly over that. We use a copper lining on the stainless steel tube. So the reactor tube wall now is copper, not stainless steel anymore. Yeah.
One more question. What is the catalyst? You were talking about catalyst. Is it composition-based catalyst or
I cannot tell you what the catalyst composition is because we're in the process of patenting it, but I can assure you it does not contain copper. And it is a spinel, and it does contain alkaline, but it contains other materials too. And it's not just the composition, it's also the method of preparation that's important to produce the results.
Dave, could I ask a question? I was at the International Conference on Reformulated Fuels 2 weeks ago after the MPRA meeting.
Yeah.
And of course, there's a tremendous concern about the concerns for MTBE, the necessity for oxygenated fuels, the requirement of domestic generated oxygenated compounds.
Right.
And what I'm wondering is, do you have a parallel program going on here, which I'm sure the tertiary alcohols might have very high octane numbers, especially the low molecular weight ones. Do you have a program going on that's sort of parallel this, that's beginning to focus on raising the proportion of these higher alcohols, just in case you're concerned about MTBE right now, but supposing...
Right, no, I absolutely agree. We would prefer that these things were just higher alcohol catalysts, and we're not making any methanol at all. Unfortunately, nature doesn't want to cooperate with us on this.
Well, methyl C5 or C6 ether is not
Yep.
bad either.
Yeah, we can make those, but we find with the catalyst at least that it really wants to maximize around the C4. And I think that's because of a steric crowding on the catalyst, although that's pure speculation on my part. But yes, we can make higher alcohols than this, but right now the yields are not exciting. But yes, I mean, that's clearly the direction that you want to go with this. The higher the molecular weight, the better. No doubt about that.
Thanks.
Thank you, Dan. Well, it's my pleasure now to introduce our plenary lecture for the symposium. It's Gary Holler, Professor Gary Holler from Yale University.